Hello! In this tutorial, we will be going over the topic of decision trees. What are they? How do they work? How are they built and trained? And what are some of their variations and limitations? Decision trees are flexible supervised machine learning algorithms. They can perform both classification and regression tasks, and even multi-output tasks. They are very powerful algorithms that are capable of fitting complex datasets and are the building blocks of random forests, which are one of the most powerful machine learning algorithms available to this day. Despite being powerful algorithms, decision trees models are among white box models. This means that it is easy to interpret their decisions and understand how they were reached, and the rules can even be applied manually if needed. This is opposed to black box models, like random forests or neural networks, which can make great predictions, but it is usually hard to explain why they were made. The model is visually represented as a tree structure, with the datasets being broken into smaller and smaller subsets as the tree grows with every decision. It predicts the value or a class of a target value based on the information from several input variables. Each decision node contains a simple true or false question about a particular input variable. And based on this, the tree splits into two branches. One represents the true subset and one the false subset. At the end of each branch is another question, and the process recursively continues until reaching the leaf nodes that make a prediction. So, to sum it up, internal nodes represent the features of a dataset, branches represent the decision rules, and each leaf node represents the outcome. We will discuss exactly how a decision tree is trained in a bit, but first, to understand well how it makes the predictions, let's follow this example. We will first demonstrate on a classification example, which uses two input variables, petal length and petal width, to predict the class of a flower. So, after training the model to classify iris flowers into setosa, versicolor, or virginica, we want to know the class of a given flower. We start at the root node at depth 0. This node asks whether the flower petal length is smaller or equal to 2.45 centimeters. If it is, then we move down to the root's left child at depth 1, which is a leaf. This means that there is no more questions to ask as we have reached a prediction and the flower is an iris setosa. In case the petal length is in fact greater than 2.45 centimeters, we proceed to the root's right child at depth 1, where we find another question about the petal width. We continue in the same manner until we reach a leaf that gives a prediction. On a closer look to one of the nodes, we find the attributes describing the features of the dataset at the particular node. The sample attribute counts for the number of training instances that the node applies to. For example, in the root's right child, 100 training instances have a petal length greater than 2.45 centimeters, of which 54 have a petal width smaller than 1.75 centimeters. The value attributes show how many training instances of each class the node applies to. The bottom left node, for example, applies to 0 iris setosas, 49 iris verdicolors, and 5 iris virginicas. This brings us to the Gini attribute, which measures a node's impurity. A node is pure when all the training instances it applies to belong to the same class. The root's left child, for example, is a pure node, as all the 50 training instances it applies to belong to the iris setosa class. Thus, its Gini score is equal to 0. This equation shows how the training algorithm, which will be discussed later, computes the Gini score of the ith node. In this equation, P of ik is the ratio of class k instances among the training instances in the ith node. Unlike linear models, decision trees can fit linearly inseparable datasets, where data points of different classes cannot be separated by a single line. Decision trees draw the boundaries iteratively for every decision node, until the whole tree is built. The decision boundaries made by a decision tree are always parallel to the axis because splits happen according to a feature that stays constant throughout each decision boundary. In our iris flower example, the first vertical boundary is drawn for the root node at petal length equal 2.45. The left side is pure, so in the next iteration at depth 1, a horizontal boundary is only drawn at the right side, separating the dataset at petal width equal 1.75. Aside from predicting the class an instance belongs to, decision trees also estimate the probability that an instance belongs to a particular class K. This is done by traversing the tree to find the leaf node for the instance and returning the ratio of class K trailing instances in the node. Estimating the probability for a flower whose petals are 5 cm long and 1.5 cm wide would output the following probabilities: 0% for Iris setosa, 90.7% for Iris verdicolor, and 9.3% for Iris virginica. A class prediction would output the Iris verdicolor class, as it is the one of the highest probability.
We use the classification and regression tree algorithm to train decision trees. The algorithm works by first splitting the training set into two subsets, using a single feature k and a threshold tk. So how does it choose k and tk? It searches for the pair of k and tk that produces the purest subset. That means we choose the pair with the lowest Gini impurity. Once the cart algorithm has successfully split the training set in two, it splits the subset using the same logic, then the sub-subset, and so on recursively. It stops recursing once it reaches the maximum depth, or if it cannot find a split that will reduce impurity. Now let's take this example. This simulation uses a heart disease dataset with 303 rows and has 13 attributes. The target consists of 138 value 0 and 165 value 1. And we only use the sex, fast blood sugar, exercise induced angina as target attributes. If we calculate the Gini impurity of these three attributes, we get that the FBS is the lowest out of them all, so we're gonna use it as a root node. As we know, we have FBS as root node. When we divide all the patients using FBS, we end up with impure leaf nodes. 165 patients with and without heart diseases in the left leaf node, and the same goes to the 133 patient in the right leaf node. Now we need to figure out how well sex and exang separate these patients in the leaf node of FBS. Exang has the lowest Gini impurity out of the rest attributes, so we will use it at this node to separate patients. In the left node of exang, we separated 49 patients, 24 of those are with heart diseases and 25 are without. Since the only attribute left is sex, we put it in the left node of exang. We do the same thing on the right branch, so we get the resulted tree in this slide. Decision trees generally are approximately balanced, so traversing the decision tree requires going through roughly log m nodes. Since each node only requires checking the value of one feature, the overall prediction complexity is big O of log 2. Now the training algorithm compares all features on all samples at each node. Comparing all features on all samples at each node results in a training complexity of big O of n times m log m. On another note, the cart algorithm is a greedy algorithm. It searches for an optimum split at the top level, then repeats the process at each subsequent level.
Alright, so diving to regularization of the hyperparameters. Alright, so as we know, decision trees are subject to adapting to the training data. By having a huge number of parameters undetermined prior to training, we can be facing an overfitted or a non-parametric model. Inversely, reducing the risk of overfitting by having a predetermined number of parameters can result in an underfitted model which its degree of freedom is quite limited. This is also called a parametric model. In order to avoid both, regularization is applied. It's a technique used to control the capacity of the model, and it's dependent on the algorithm exhibited. In simpler terms, best fitting model generally done via restricting the maximum depth of the decision trees, like having a certain range by increasing the minimum hyperparameters or reducing the maximum hyperparameters will regularize the model. Some famous parameter used like min samples split. This is the minimum number of samples as node must have before it be splitted. Minimum samples leaf, the minimum number of samples a leaf node must have. Minimum weight fraction leaf, same as minimum sample leaf, but expressed as a fraction of the total number of weighted instances. Maximum leaf nodes, the maximum number of leaf nodes, and max features, the maximum number of features that are evaluated for splitting at each node. Alright, so some algorithms regularize hyperparameters in other ways, by first training the tree with no restrictions, then pruning unnecessary nodes in order to best fit the model. For example, a node whose children are all leaf nodes is considered unnecessary if the purity improvement it provides is not statistically significant. A standard statistical test, such as the chi-squared, which is shown in the slide, are used to estimate the probability that the improvement is purely the result of chance. If this probability, called the p-value, is higher than a given threshold, typically it's 5% controlled by the hyperparameters, then the node is considered unnecessary and its children are deleted. This pruning process continues until all unnecessary nodes have been pruned. Moving to regression trees. So in general, decision trees are also capable of performing regression tasks. So what is regression? Regression is a problem of predicting a real valued label, often called a target, given an unlabeled example. A regression learning algorithm takes a collection of labeled examples as inputs and produces a model that can take an unlabeled examples as input and output a target. This tree shown in the slide is predicting the value on each node. It's very similar to the classification tree we've seen earlier. The main difference is that instead of predicting a class in each node, it predicts a value. For example, suppose you want to make a prediction for a new instance with x equal 0.6. You traverse the tree starting at the root and eventually reach the leaf node which predicts value equal 0.111. This prediction is the average target value of the 110 training instances associated with the leaf node, and it results in a mean squared error equal to 0.015 over these 110 instances. So in this slide, we can see the predictions of the previous model shown in the figure on the right. We can notice that the predicted value for each region is always the average target value of the instances in that region. The algorithm splits each region in a way that makes most training instances as close as possible to the predicted value. The CART algorithm works mostly the same way as earlier, except that instead of trying to split the training set in a way that minimizes impurity, it now tries to split the training set in a way that minimizes the MSE. Just like every decision trees and classification tasks, regression trees are also prone to over or under fitting. Without any regularization using default hyperparameters, you get the prediction on the left, which is obviously overfitting the training set very, very badly, actually. This example shows a regularization parameter using mid-sample leaf to output a more reasonable fitting model, which is on the right.
Decision trees have orthogonal decision boundaries, which makes them sensitive to training set rotation. For example, this figure shows a simple linearly separable dataset. On the left, a decision tree can split it easily, while on the right, after the dataset is rotated 45 degrees, the decision boundary looks unnecessarily convoluted. This means that a small change in the dataset can make the tree structure unstable, which can cause variance. Also, decision tree learners create underfit trees if some classes are imbalanced, so it is therefore recommended to balance the dataset prior to fitting with the decision tree.